Well, hello, back again. This is going to do chapter 30, Cosmological Difficulties of Newton's Theory. This is also called part 3, Considerations of the Universe as a Whole. So I'm just going to crank through these videos because it's raining outside today and I don't feel like going outside. So might as well take advantage of that fact and we might even be able to, who knows, might even be able to finish this book today. Uh, and then go on to something else. But I'm going to just go ahead and read this as I usually do and see if we can understand what's going on here. Um, so this chapter, just looking at it, looks like okay. So Einstein's saying that there's difficulties in Newton's theory. He seems to say that a lot in this book, and we are gonna read this and see what happens. All right. So Einstein says, apart from the difficulty discussed in section 21, there is a second fundamental difficulty attending classical celestial mechanics, which, to the best of my knowledge, was first discussed in detail by the astronomer Seeliger. Seeliger. Alexa, who is? Oh, wait a minute. Alexa, who is Seeliger?
According to an Alexa Answers contributor, SHERE is an archaic spelling of sheer.
Alexa, stop. Alexa, who is Seeliger?
According to an Alexa Answers contributor, SHERE is an archaic spelling of sheer, acceptable in the Middle Ages for any form that was
Alexa,
not
stop. I got a kind of a cold, so I think Alexa doesn't understand what I'm saying. But I don't know. Let's ask Google.
The mic's back on.
Hey Google, who is Seeliger?
According to Wikipedia, Hugo von Seeliger, also known as Hugo Hans Ritter von Seeliger, was a German astronomer, often considered the most important astronomer of his day.
So if we ponder over the question as to how the universe considered as a whole is to be regarded, the first answer that suggests itself to us is surely this. As regards space and time, the universe is infinite. So if you look up there in the blue sky or stars, whatever, you just go and you keep going and you keep going and you keep going and nobody knows where the end is. That's the idea of there is no end, maybe, but it may curve on to itself. We'll see. Let's see what see what Einstein says. There are stars everywhere, so that the density of matter, although very variable in detail, is nevertheless, on the average, everywhere the same. In other words, however far we might travel through space, we should find everywhere an attenuated swarm of fixed stars of approximately the same kind of density. This view is not in harmony with the theory of Newton. The later theory rather requires that the universe should have a kind of center in which the density of the stars is a maximum, and that as we proceed outwards from this center, the group density of the stars should diminish until finally, at great distances, it is succeeded by an infinite region of emptiness. The stellar universe ought to be a finite island in the infinite ocean of space. And there's a footnote here. It says proof. According to the theory of Newton, the number of lines, quote, lines of force, unquote, which come from infinity and terminate in a mass m proportional to the mass m, if on average the mass density rho zero is constant throughout the universe, then a sphere of volume v will enclose the average mass rho zero times volume. Thus, the number of lines of force passing through the surface f of the sphere into its interior is proportional to rho zero v. The unit area of the surface of the sphere, the number of lines of force which enters the sphere is thus proportional to rho zero v divided by f, or to rho zero times r. Hence, the intensity of the field at the surface would ultimately become infinite with increasing radius r of the sphere, which is impossible. Okay, that's a little sidetrack, I guess, by Einstein. This paragraph kind of reminds me of the Big Bang Theory. I guess the having no mass concentrated, then boom, it blows up, and here we are. I don't know if that's true or not. But anyways, this this conception is in itself not very satisfactory. It is still less satisfactory because it leads to the result that the light emitted by the stars and also individual stars of the stellar system are perpetually passing out into infinite space, never to return, and without ever again coming into interaction with other objects of nature. Such a finite material universe would be destined to become gradually but systematically impoverished. In order to escape this dilemma, Seliger suggested a modification of Newton's law in which he assumes that for great distances the force of attraction between two masses diminishes more rapidly than would result from the inverse square law. In this way, it is possible for the mean density of matter to be constant everywhere, even to infinity, without infinitely large gravitational fields being produced. We thus free ourselves from the distasteful conception that the material universe ought to possess something of the nature of a center. Of course, we purchase our emancipation, our freedom, from the fundamental difficulties mentioned at the cost of a modification and complication of Newton's laws, which is neither empirical nor theoretical foundation. We can imagine innumerable laws which would serve the same purpose without our being able to state a reason why one of them is to be preferred to the others. For any one of these laws would be founded just as little on the more general theoretical principles as is the law of Newton. And that's it for this chapter. The section next one is 31, the possibility of a finite and yet unbounded universe. So that was an interesting little chapter. Uh, so yeah, I always look up in the sky. You see how far can you go? It's like I can only go like one arm's length. You know, you can always jump up, or you go in a rocket ship and see how far you go. But farthest we've been. Hey Google, what's the farthest humans have been in space?
Sorry, I don't have any information about that.
Alexa, what is the farthest a human has been in space?
According to an Alexa Answers contributor, currently, the farthest humans have traveled in space is from the Earth to the Moon and back. The distance from the Earth to the Moon is 238,900 miles.
Hey Google, what was the farthest distance in Apollo 8?
According to Wikipedia, Apollo 8 achieved a maximum distance from Earth of 203,752 nautical miles.
That's as far as we've gone, pretty much. Well, probably gone a little bit farther, but yeah. So we haven't gone very far compared to infinity. But yeah, we don't really know. Nobody knows. Nobody knows really how far you can go out that way, or this way, or that way, or this way, whatever, whichever direction. It's kind of funny. Up and down, up on one side of the Earth is the opposite of. Never mind. Flat Earth people. If you're a flat Earth person, up and down is probably pretty confusing. But anyways, so we'll keep burning through this pretty quickly. We're getting see if we'll take advantage of the rain today and see if we can get all the way through this. You take care of yourself and have a good evening, good morning, good day, good whatever. You take care. Bye.